Hello there, everyone, and welcome to this weekly presentation of Morrison Planetarium's Tour of the Universe, live and direct from the California Academy of Sciences in San Francisco, California. Thank you very much for joining us from wherever you are, and we'd appreciate it if you could just let us know your location in the comments. Now, we occasionally have viewers tuning in from the UK and India and other parts of the world, and we'd love to know where you're hearing from today, or tonight, or this morning, as the case may be. As always, if you have any questions, please feel free to drop them in the comments, and we'll try to respond to them or maybe give you some leads as to where you might be able to find the answer. Our vehicle for this trip through the universe is the astronomy visualization program OpenSpace, which is supported by NASA and which is available as a free download from OpenSpaceProject.com. If you like what you see on your screen, you can install this very same program on your computer at home and fly through the universe. The download link will list the hardware requirements for the optimum performance. Again, OpenSpaceProject.com. And we also have a link to a survey where you can tell us what you think of the software so the developers can use that feedback and improve the program. OpenSpaceProject.com. And with that, let's take off on a trip to outer space. Now, we're presently looking at something that is about 250 miles above the Earth, or 400 kilometers high. That is the International Space Station, which is as far as humans travel from Earth right now. Now, a number of years ago, one famous astronomer, British astronomer named Fred Hoyle, said, outer space isn't remote at all. It's only an hour's drive if your car could go straight up. And that's because the internationally recognized boundary of outer space is 100 kilometers or 62 miles above the Earth. Back in 1952, it was calculated to be about 50 miles high, or 80 kilometers. And for some purposes, that's what NASA uses. But it turns out, though, there really isn't a hard and fast number that you can put on the edge of space, because that may vary depending on the expansion or contraction of Earth's atmosphere, and there's no sign hovering up there in the sky that says, "Welcome to outer space." So what makes that altitude so special as to be considered the boundary of space? Well, basically, it's because the atmosphere is so thin up there that air-controlled surfaces like wings and flaps and rudders don't work. That high up, you need rockets to maneuver. So 100 kilometers above the Earth, the view is pretty good from up there. But 4 times that, up here at 400 kilometers, the view is getting pretty spectacular. Now, the International Space Station is the largest thing ever built in outer space. Its construction began around 1998. It has been continuously occupied by members of the 16-country consortium that built the space station, or the ISS. It's been continuously occupied since about 2000. Rotating crews of about 6 to 7 people, and they stay for about 6 months at a time in this home away from home. The internal volume of the space station is about the same as a 747, although the entire footprint, including the big solar panels, is roughly the size of an American football field. So it is a very, very big object. And if it passes over your location on Earth, it is big enough and relatively low enough so that you can see it with the unaided eye from the surface of the Earth. If you are lucky enough, you can find out where the space station is supposed to be in the sky. There are plenty of apps and websites where you can look up this information for ISS predictions. And you can find out when it's going to pass over your location, and you can see it for yourself in the nighttime sky with the unaided eye. It is sometimes a brilliant object, as bright as the planet Venus. So try looking for that, the International Space Station, as it passes overhead. Speeds around the Earth at a velocity of about 14,000 miles per hour. That's about 5 miles a second, and circles the planet about 90 minutes. Once every 90 minutes, rather. So it is a beautiful and spectacular object. But as we travel farther away from the space station, we're going farther than humans currently travel. And we are actually going to go to our satellite, the moon, which is the farthest that humans have ever traveled. And that was about 50 years ago, back during the Apollo program of the 1960s and 70s. And to find the moon, I'm going to have to bring up the orbit of our satellite so that we can actually see where it's supposed to be. Let's see here. Moon orbit should be there. Okay, there's the moon's orbit. So I'm going to rotate around and have a look at the moon, focus on the moon, zeroing in on it, and we'll zoom up to our satellite, our nearest neighbor in space, which is about 250,000 miles away. Now we're looking at the moon at an unusual phase. Actually, we're showing it at a new phase right now. So I'm going to turn around and turn on some illumination, turn off that shadow so we can see the side of the moon that we normally see from Earth. That looks like a more familiar view. So let's have a look at our satellite. The farthest that humans have ever traveled, that was back between 1968 and 1972. The moon is a large ball of rock about 2,000 miles across. It's very dry. It has no atmosphere, no bodies of water, no weather, no life. Its surface is covered by thousands and thousands of craters. As you can see, those craters were blasted out by the impact of asteroids, comets, and meteoroids in the past several billion years. Some of these craters are very large, some measuring dozens of miles across, some hundreds of miles across. Many are very small, too small to be seen from the Earth, even with telescopes. But the 12 Apollo astronauts who walked on the surface of the moon were able to study the moon, walk around, leave their footprints in the lunar dust, and collect samples and brought them back to Earth. And hopefully, NASA wants to do that again in the next few years with the Artemis program, which is currently testing out the hardware for that effort. You might have heard in the news where NASA recently tested the Orion spacecraft, which is the space capsule which will take future astronauts back to the moon, and NASA says to stay. Well, we can see the surface of the moon, very dry, very cratered, very rocky, and these craters here make the moon look like a very forbidding place because it's been bombarded over billions and billions of years. Those dark patches that we now see are called the Maria, lunar Maria, which is from the Latin, and it means seas, because early astronomers thought that these were bodies of water. So they called them the Sea of Rains, or the Sea of Tranquility, or the Sea of Serenity. But these so-called seas are actually large, flat plains of dried rock. Molten magma bubbled up from below the surface several billion years ago, spread out, cooled, and hardened into these flat, dark plains. And subsequently, later craters, more recent asteroid impact, formed the small craters that we now see. But the moon is still a really fascinating place, geologically speaking. When I was a kid with my first telescope, I could stare at the moon and look at it for hours on end on a nice clear night. Well, that's our satellite, the moon, and it took the Apollo astronauts about 3 days to get there. That was 50 years ago. It takes a beam of light or radio signals even less time to get to the moon. From the Earth to the moon, about 240,000 miles. It would take a beam of light, which travels 186,000 miles per second. That beam of light would take only 1.5 seconds to get to the moon. And when we talk about the distances to objects far off in space, astronomers like to use the speed of light as a different kind of measuring stick instead of using miles or kilometers, because the distances to things in outer space is so huge that measuring them in miles or kilometers gives us numbers that are just so big and unbelievably large, it's hard to comprehend. So astronomers use the speed of light. How long does it take the speed of a beam of light to get from one place to another, from the Earth to the moon, or from the Earth to the sun? Here's our planet, the Earth, with the moon circling around it again. And let's back off away from our planet and have a look at where we are in the solar system. And we are the third planet from our star, which is at the center of the solar system. Coming into view now at the bottom of your screen is the sun, with the planets, the orbits of Mercury, and then Venus, and we on the Earth are third, and fourth comes the red planet Mars. So those are the four inner planets, or the terrestrial planets, the rocky planets, as they're also known. After Mars is a big gap that is filled with lots of chunks of material. These are chunks of material that were left over from the formation of the solar system. This is the main asteroid belt, which contains several 100,000 asteroids so far, but there may be as many as 1 million. And there are many other asteroids that wander outside of this zone as well. Following the asteroid belt come the orbits of the giant planets, Jupiter, Saturn, Neptune, and Uranus. Those are the 8 planets that orbit our star, the sun. Now, there are a number of spacecraft that have since left our solar system, starting in 1973, and we can show you the paths of some of those spacecraft as they have left the Earth. The one going off to the top all by itself is Pioneer 10, which was launched back in 1973. And then after that is Pioneer 11 going off in the opposite direction, Voyager 1, and Voyager 2, which took a downward turn after it passed Neptune, right there. And then the shortest path is New Horizons, which passed Pluto in 2015. Those are the 5 spacecraft that have left our solar system, basically, going way beyond the orbits of the outermost planets. And those are our most distant physical emissaries from Earth, although they're not the most distant artifacts of humanity that have left our planet. One more thing I should show you before we get too far away. Let me zoom back in toward the solar system and show you another zone of material, another belt of debris, which surrounds the solar system, sort of like the asteroid belt, only bigger and quite a bit messier. This is called the zone of trans-Neptunian objects, or the Kuiper belt, after the astronomer Gerhard Kuiper, who theorized its existence. And this is full of short-period comets and other objects, mini planets like Pluto, and a few other objects out there. So there's a lot of stuff in our solar system, and this is just a small part of that collection of material. But now, as we travel farther out from our star, the sun, we'll start to move between the stars, excuse me, and traverse interstellar space. And before we get too far away, we'll start to see ourselves moving among the stars. And as we do, our perspective changes and familiar constellations begin to lose their shape. So constellations don't look the same when you're traveling way out in space this far. And this far out, we can encounter one more artifact of humanity, our footprint in the universe, and that is a bubble of radio noise that surrounds us called the radiosphere. For about the past 90 to 100 years, Earth has been sending out radio signals, not intentionally, at least not at first, but these were stray radio signals that leaked out through our atmosphere, and traveling at the speed of light, they crossed 90 light years since that time and now form this giant sphere around us. Excuse me. And this is as far as any evidence of humanity has extended into the universe. It continues to expand outward at about 1 light year per year. A light year is the distance that light travels in 1 year, or about 6 trillion miles. So this is our signature. It's us saying hello to the rest of the universe. And notice that there are some stars inside the radiosphere. If there are any civilizations orbiting those stars, if they have the technology to detect our radio signals, they might have heard those signals. They could be listening to our earliest radio signals right now, and they would know about us. But if they're outside the radiosphere, our radio signals haven't gotten to them yet. So if there's anybody out here this far, they wouldn't even know about us. And this is not even a large portion of our galaxy. We're still in a very, very small enclosed part of the Milky Way galaxy. Let's travel even farther out so we can see where we are in the Milky Way. Up to about 100 years ago, astronomers thought there was only one galaxy in the entire universe, that being the Milky Way. But Edwin Hubble, an American astronomer, showed astronomers proof that there are other galaxies far outside the Milky Way. Not only that, he showed them evidence that those galaxies are all moving apart from each other. Not only was the universe bigger than just one galaxy, it was getting even bigger still. The Milky Way is a huge, flat, spiral-shaped disk of several 100 billion stars. You can see how flat it is as we pass through the pole, or pass through the plane. I've still got the radiosphere highlighted there so you can see where we are in the Milky Way. We're nowhere near the center. We're about 2/3 of the way out along the edge of one of the spiral arms, way out here. The Milky Way is just one member of a small cluster of galaxies called the Local Group, which contains about 80 galaxies in all, two very large ones, the Milky Way and another galaxy called the Andromeda Galaxy. Those are the two largest members. And the Andromeda Galaxy is a galaxy that we can see in the night sky with the unaided eye, just barely. And even though it's the nearest large galaxy to us, it's about 2.5 million light years away, which means that the light of that galaxy takes about 2 million years, 2.5 million years to reach us here on Earth. When we look at the Andromeda Galaxy in the sky, we're seeing light that left it 2.5 million years ago. And we're looking at what that galaxy looked like 2.5 million years ago. If you want to know what it looks like right now in 2022, you have to be patient. You have to wait another 2.5 million years for that light that's leaving it right now to get to us, crossing that distance to the Milky Way. And that's how big the universe is. You know, Douglas Adams put it pretty well. He said, the universe is big. It's really big, unbelievably big. And as we back away from the Milky Way and the local group, we start to see other objects out there, which now, since we've left the Milky Way galaxy, these are not stars that you're looking at. Every spot that you see on your screens right now is not a star, but a whole galaxy. And these are the locations of galaxies based on surveys of the universe that have been taken over the past several decades that show us where the galaxies are in relation to one another. So we can see that the galaxies are not very evenly distributed across the universe. They're clumped together into groups, clusters, superclusters with thousands of galaxies in each supercluster. And these superclusters form threads, filaments, and tendrils, as you can see, just separated by large voids of empty space. Again, this is real data. This is what the universe really looks like, the large-scale structure of the entire universe. As we back away, our map of the universe, the model that we've developed from all the data that we've taken, shows us a very unusual shape. The model of the universe that we follow today looks rather unusual. And what does that tell us? Well, it tells us that our survey is incomplete, because does the universe really look like this? Does it really look like a giant butterfly or two cones touching tip to tip? Well, no, that's not the real shape of the universe. The reason our map, our model of the universe looks like this is because that empty area, the space between the two cones, is not empty space. It's actually areas that we haven't mapped very well yet, because there's something blocking our view. And what's blocking our view is our own Milky Way galaxy, the dust and gas in the Milky Way preventing us from seeing what's farther out beyond. And so that's why that gap is there. Eventually, though, as our technology and techniques get better, they improve, we'll be able to fill out our map and find more galaxies more evenly distributed throughout space all around us in every direction. Now let's travel farther out in space. Excuse me again. And when we look out this far into the universe, we're seeing across perhaps 10 billion light years. And we're beginning to see objects so far away that their light took 10 billion years to reach us here on Earth. Those objects, called quasars or quasi-stellar radio sources, are the orange objects that you see at the ends of the cones or fans. And those are objects that are very, very bright as astronomers see them. And astronomers figured out how far away they are. And from that distance, to be so bright, they must be tremendously energetic. And astronomers now believe that quasars are the centers of very young, newborn galaxies powered by supermassive black holes, which we're only beginning to understand. And surrounding everything, coming from all directions, is the farthest thing that can be detected, and that is a faint radiation that permeates the entire universe. It's called the cosmic microwave background, and it's believed to be the first light that was able to travel from one place to another in the universe. When astronomers determined that the universe was expanding, getting bigger and bigger, they did some calculations and backtracked where that expansion should have begun, and they came up with a figure of about 3.8 billion years. And backtracking that, they calculated how hot the universe should have been with everything compacted so close together. And they say that at the earliest time we can measure, the universe was very dense, very hot, very opaque, and light could not travel from one place to another. But then the universe suddenly began to expand. It turned into something more transparent, more rarefied, and much cooler. And light began to be able to travel from one place to another. And that light is this cosmic background, cosmic microwave background that we see coming from all directions. That is what astronomers say is the best evidence for what has come to be known as the Big Bang, which is the moment that the expansion of the universe began. And this is the farthest thing that can be detected. And this is the edge of the visible universe as far as we know. And that being the case, we haven't any farther to go. So we have to go back in toward where we came from. And as we do that, it may occur to you that as we travel back to where we started from, the universe seems to be centered on us, on where we are from Earth. Are we really the center of the entire universe? Might be a nice thought for some people, but no, we're really not. The reason our model of the universe has this shape, that shape of a fan or an hourglass or a butterfly, that's because we're the ones who made the map. And it's based on our perception of where we are and of the distribution of things all around us. If there were someone somewhere else in another part of the universe making their own map, their own model of the universe, it would look very similar with them at the center of their model. But we don't really know if the universe even has a center. As we travel back in toward the beginning of our journey, we'll approach the local group. We'll approach the Milky Way galaxy. There we are, our flat galaxy. As we approach it, we see our radiosphere indicating our location on the edge of the galaxy's spiral arms. And as we travel in, after all the galaxies and stars, after all the amazing things we've seen, you might wonder, are there any other planets out there in space? And actually, according to astronomers, yes, there are. There most certainly are. And these objects are called extrasolar planets, or exoplanets for short. And here is a current map of the known locations of stars that are orbited by at least one exoplanet. And so far, since about 1994, astronomers have detected more than 5,000 other planets outside our solar system. 5,000 other places where possibly life could take hold. It's not likely that all of these planets might have life, because we know that some of these planets are very the wrong type of planet. They're very gaseous, very large, like Jupiter. Others might be small and rocky, but they might orbit the wrong kind of star. They might orbit a star that is too hot, has too much radiation that might be harmful to life. So for a planet to be able to support life, it has to be the right kind of planet. We think it has to have a solid surface. It has to orbit the right kind of star. It has to orbit at the right distance from its star. It can't be too close, can't be too far away. The temperature has to be just right for liquid water to be able to exist, because liquid water is what we believe is necessary for all life to exist as far as we know. That supports the chemistry of life. And a planet has to be made of the right components that will allow the nutrients of life to exist in its environment. And so there are a lot of things that planets need to be able to support life. And so far as we know, there's only one that fulfills all those conditions. And it's the one we came from, the planet Earth. Out of all the planets we've seen, orbiting all the stars in all the galaxies that we've seen, our planet Earth, as far as we know, is a place that's unique in the universe. It is the only one that we know of that has life thriving on its surface. And so, traveling to the edge of the universe and back, traveling through the stars and galaxies, we find that there is truly no place like home. And returning home, welcome back to the planet Earth, the place where we came from. And with that, we'd like to thank you all very much for joining us on our journey through the stars. Our world is a very special place. It's one that we want to take good care of, and it's a place that makes us realize that it is a very unique and special thing that we need to preserve and protect as much as we can. We wish happy holidays to all watching today, and we appreciate your support, and we invite you to join us online every Wednesday at this time for Morrison Planetarium's live tour of the universe.